Welcome back to How to Program. Just a warning, this show is best viewed in order. If you have not started in order and watched the previous episodes, I recommend you do so by clicking on our channel and starting with the very first episode. I promise you things make a lot more sense when you go in order, and they were set up this way. So go ahead and do that if you haven't done it before. This episode is episode number 7. We're going to talk about binary, and we're going to talk about common sizes and limits in binary. Now, I've been teaching you guys binary for a few episodes now, but I realized I never really explained why this was important to program. Like you guys want to program. This is how to program after all. Well, look, binary is how a computer stores its data. It is. So if you don't know how to do that, or how it stores its data, then that's going to be a missing sort of fundamental thing that you're not going to know, and you're going to be sort of confused about later things that we're going to talk about. So it's important to know as a basic thing. It's a basic part of computer science. Computer science is the science of dealing with computers and programming and all of this. And the weirdest bugs that you get, errors in your code, usually occur with issues relating to how data is stored in binary. So if you already know how data is stored in binary, when you see this bug, it'll click. It'll go, oh, aha, oh, yeah, I know. This is an issue because I didn't store it right in binary or something, like it has to do with binary. So it's a good thing to know. You do need to pay attention to the limits of various variable types. Variable, those places in memory where you're storing your data. These have limits, and the limits come from how the data is stored in binary. So now that you kind of understand how data is stored in binary for most things, we're going to look at the limits. I've said this word before, but I don't think I've defined it. A bit is just a single 1 or 0 in a binary number. So 1 bit, 1, 1, or 0. Usually abbreviated as a single lowercase b, like you say 16 bits, you might write 16b with a lowercase b, or you say 8 bits, you might write 8b with a lowercase b. There's another word which is very similar to bit, but is not the same word. It's a byte, B-Y-T-E. And a byte is 8 bits grouped together as a unit of memory. So it's 8 bits. The smallest unit of memory that you can use as a variable in most types of computer code is a single byte, or 8 bits. Like if you want to represent a Boolean value, and you know that a Boolean value only has 2 possible values, it's true or false, right? So you're like, well, I just need a single bit. Yeah, well, the computer doesn't care that you need a single bit. The lowest amount you can get is 8 bits, is a single byte. So even if you only want to represent a 0 or a 1, you're getting a whole byte to do that. And that's okay. That's the electronics are just set up that way. It's just faster for the processor that way. So that's okay. Now, if we're dealing with bytes, we usually abbreviate it with a single uppercase B. Like if we said 1024 bytes, we would say 1024B with a capital B this time. Or 32 bytes, we would say 32B with a capital B. Now let's take a look at the sizes of memory and what you can store with that amount of memory. Well, with a single byte, you can store a single small number. It's 8 bits, so like a small number would fit in there, but not a very large one. If you had a kilobyte, kilo means 1,000, you could store a small piece of text in that, like maybe a little short email or something, or a tweet, for definitely a tweet, 140 characters, you could store that in a kilobyte. Now a megabyte is a million. Mega means million in this word here. You could store a photo, probably low quality these days because photos take up a lot of space, but you could store a photo of low quality in a single megabyte. Now gigabyte, now we're starting to get into larger numbers, so that's a billion. And giga means billion in this case. So a single episode of a TV show usually fits in a gigabyte. Maybe even a whole movie if it's not very high quality. Now a terabyte, this is usually the unit that you look at when you're buying hard drives these days. And a terabyte, tera means, 1,000, like 1,000 gigabytes. It just goes up, right? So in a terabyte, you can store a collection of many movies on a single, like it's a hard drive. Basically, hard drives come in 1, 2, 3, 4, up to 6 terabytes these days. Now there's a next level up is a petabyte, and that's 1,000 terabytes. So picture 1,000 hard drives, you know what I mean? And that's for very, very large sets of data. For example, for Facebook, Amazon, Google, they often deal in sizes of petabytes for all their users' data or all their photo sizes or whatever. It's a lot of data. And then exabyte, allegedly this would be all words ever spoken by human beings, could be stored in approximately 5 exabytes of data. I don't know if this is true or not. Obviously, we've spoken a lot of words, but there's just a number that it's hard to wrap your head around how big that number is. You know what I mean? There's a lot of data that can be stored there. So, just a lot of data there. Now, let's take a look at a simple example with 1 byte, 8 digits, 8 bits. And the biggest unsigned binary number, no 2's complement here, just a single unsigned binary number, we could store in 8 bits is all ones, which is 255 in decimal. Now what happens if you try to store a number that's bigger than 255 in a single byte? Let's try to store 256, and that's a 1 followed by 8 zeros. So if we were trying to fit this, if we try to fit it in a single byte, 8 bits, we would get the rightmost 8 bits and would cut off the 1. So we would get all zeros, which is not what we wanted. We wanted 256, but we got 0. So that doesn't work. This is an error, and it's called an overflow error because we ran out of space to represent our numbers, so the number gets cut off and we get an unexpected number. We talked about this a little bit when we dealt with negative numbers, but it's just a good review. Now, there's a word here that you're going to see next in the next slide, and I wanted to define it beforehand. It's an integer, pronounced integer. It means a whole number. No fractional parts, no nothing. It's just a whole number, positive, negative, or 0, usually, that you have. So let's take a look at the common variable sizes and names. Remember, variable is a unit of memory. So when you're asking for memory that can store numbers, these are the names you're going to be telling the computer so that you can get what you want. So if you want a single byte of 8 bits signed with a sign, 2's complement, you are going to ask for a byte. And you're going to get 1 byte or 8 bits. And the minimum value you're going to be able to store is -128, and the maximum value is 127. Now remember, there's 256 possible values that you can store there. And that's fine, but the maximum numbers are different than the total number of values that you can store, of course. So the next thing we're going to look at is a short. This is a short integer. A short integer is going to be, in most systems, is going to be 2 bytes or 16 bits, and you're going to be able to store, when it's signed like this, minus 32,768 to positive 32,767. Just make a note here, when the number is signed, it's just the name of the thing, like the short name, like the actual name you're going to put in the computer, byte, short, int. These are not, they don't have anything in front of them. That's just the thing. So when you're telling it to give you a number, by default, it gives you a signed number because it assumes you want to be able to represent signs. So that's fine. An int in most systems is 4 bytes or 32 bits, and that gives you, negative 2 billion to positive 2 billion with a bunch of stuff after it. And then a long is going to be 8 bytes or 64 bits, and that's going to be -9 quintillion to positive 9 quintillion, and a bunch of stuff after that. That's a very large number, very, very large number. Now, if we look at unsigned, so now removing the 2's complement thing in there and just getting a whole unsigned number, you're going to get a byte. With a byte, you're going to be able to store from 0 to 255. With a short, you're going to get the same amount of memory, except this time it's not in 2's complement, so you can store positive numbers only in that range, right? So with an unsigned short, you're going to get from 0 to 65,535. With an unsigned integer, you're going to get from 0 to 4 billion, something. And with a long, unsigned long, you're going to get from 0 to 18 quintillion. So why don't you always use the biggest size? Some people have asked me this before. There's a lot of reasons why you don't want to just always use a long for every single number you store. Historically, computers had a lot less memory, so that it mattered a lot more than it does now, but it still matters because, for example, on smartphones, you have very little memory. Smartphones still don't have as much memory as desktop computers do, or laptop computers. Also, there's a lot more what I call the Internet of Things. You know, that whole Internet of Things is like little tiny computers and everything, like in your thermostat, or to turn on your lights, or, you know, to open your garage door, and it's all got a little computer in it that's connected to the internet or something, you know. Well, all those little systems are not going to have a lot of memory. They're going to have maybe 32 megabytes, 16 megabytes, 8 megabytes. Like they might have very, very little memory. You know what I mean? So then it will really matter what size you use in your program. It also matters when you're storing a lot of data. Like if you're repeating data of the same size over and over, like you're storing, you know, the age of a person, but you're storing millions of people, then you're storing that age number millions of times. If you pick a long, that's just a waste of space. You know, an age for a person is never going to go above like 125 or something like that. You know, like the oldest person was like 124, 125, something like that. So, you know, you could get away with a single byte. So why go anything else? And then you also know you don't need a signed number because no one has a negative age. So why use a signed number? So you should use an unsigned byte if you know that you can use it. You know what I mean? So be smart about these things. You should always pick a size that works for you. You shouldn't just necessarily try to pick the smallest size, because I think that can lead to the other problem, which is like you get a weird bug because your integer or whatever is too small, or your number is too small. You know, like the size in binary is too small, and then it overflows or something, and you don't want that. You know, so don't be too conservative, but also don't be like crazy and always pick a long. Okay, so that covered sizes of numbers and so forth. The next lesson is probably one of my favorite ones so far. We're going to talk about how numbers with a fraction are stored in binary. And this lesson is probably the one that requires you to have everything before it really well in mind. So if you want to review all the videos in binary, or on the subject of binary up to now, before you watch the next one, it's not a bad idea. You know, and they're not that long, and you should really do it if you're unsure about anything, or if you need to do more examples on a piece of paper or something, like really get it, because the next one is going to be pretty intense. So I hope to see you next time for this particular lesson, because it will be very exciting. And you can also like our Facebook page to get updates as soon as the episodes come out, and I really recommend you do that. And if you really like our channel, you can also like the video, comment, and subscribe, and let us know that you like it. All right, we'll see you next time.